Now we want to go over one of the very important tests for convergence, known as the integral test. Okay, so this is going to use this relationship between integrals and sums to kind of be able to kind of flip back and forth between the two when we're showing convergence. So we tried to show convergence for similar types of integrals, right, with improper integrals, where we showed the integral from some number to infinity. So in a sense, that's not too far off from what we're doing here with the series, right? With the series, we're trying to show that the sum of some sequence from n equals 1 to infinity is convergent. And then with the integral, maybe we could show from 1 to infinity of maybe some function instead. Maybe you call it f sub n or f of x or whatever. And, because integrals are basically, in a sense, they are infinite sums, right? They're the infinite sums of those rectangles of the area of each of those infinitely small rectangles underneath the curve, right? So these, they kind of share the same bones, I guess I would say, right? Now, they're not quite exactly the same thing. Namely, this only goes over the integers, whereas this goes over all real numbers, and that does make a huge difference, especially when you really start, studying the like the real line and what we call analysis. You see that there's actually a pretty huge difference between these two. So they're not going to be exactly the same, but we can, for this purposes of convergence or divergence, we can switch between them under certain conditions. Okay, so I'm just going to write out the definition of the integral test first, or just what this test is first, and then we'll look at it more in depth here. So suppose that n equals 1, sum of n equals 1 to infinity of a sub n is a series with positive terms. Okay, so the first important condition here is that the terms, these a sub n terms, they must all be positive. Okay. Suppose there exists a function call it f, and a positive integer n such that the following are true. Okay, so we're going to have three conditions here. One, f is continuous. Okay. So we need this function f, which we haven't even put any conditions on it, but whatever this function is, it needs to be continuous. Two, f is decreasing. Okay, so it specifically has to be decreasing. And then three, f of n is equal to a sub n for all integers n greater than or equal to capital N. So this last statement is just basically saying that f of n, the function and the sequence, have to be the same only at the integers after a certain point. So it doesn't need to be the whole time, right? Like it doesn't need to be for the first 10 terms. It could be a different function for the first 10 terms, but then it is the same for the next, after 10, from 10 to infinity or something like that. But after a certain point, it has to be the same always. Okay, even if it's at the millionth integer, at n equals 1,000,000. From that point on, it needs to be the same. Most of the time, it'll be the same right away, the ones that we'll use here. So if we have these three conditions, then the sequence of a sub n, well, the sum of a sub n, I should say, and the improper integral from where those terms start being the same to infinity of f of x dx both converge or both diverge. Okay. So they either both converge or they both diverge. Okay, so again, maybe not super surprising that they would behave similarly because, again, integral is a type of sum, right? So these are both kind of, in a way, infinite sums. Again, they're not the same because this one only goes over the integers. This one is going over all real numbers. And that's reflected in the fact that just because they both converge, this does not imply that they are converging to the same number. Okay, so it's only telling us that if the integral does converge, then the sequence will also converge. But it doesn't tell us what number the sequence is, or the sum, I should say, is converging to. So usually when we calculate the improper integral, we're able to actually calculate what number it's converging to. We can actually calculate the value of the integral fairly easily. But with the sum, it's not necessarily quite so simple to calculate that number, and we can't say it's the same number. It's probably not the same number because, again, this is finding the area under, like, this is going over all real numbers, whereas this is not. Okay, and that makes a huge difference. So one of the big candidates for this then would be this harmonic series, 1 over n. Okay. The integral from 1 to infinity of 1 over x, rather, dx would correspond to this, and it would fit all of the conditions. Okay. So on 1 to infinity, this is continuous. Okay. It's not continuous over the entire domain, but it only needs to be continuous on this interval. Okay. It is decreasing. Okay. It would be, 1 to, if you really wanted to show it, like if you really want to show this is decreasing, you technically would need to show it with the derivative. The derivative of 1 over x is negative 1 over x squared. And this is going to be decreasing for any positive number, right? It's going to be negative for any positive number. It's actually going to be negative for any number. And this is clearly equal to 1 over n for the integers, right? Because they're the same function, just the domains are different, right? This is only going over the integers. Again, this is going over all the real numbers. But at the integers, they will be the same. So if we can show that this converges or diverges, then that'll tell us whether this one converges or diverges. So let's go ahead and do that. So let's just do it first, and then I'll go ahead and show like kind of why this is true, geometrically speaking. Okay, so we'll look at the integral from 1 over x, or 1 to infinity of 1 over x dx. So if you remember, this is going to be the limit as b goes to infinity from 1 over b, 1 over x dx. Okay, so we just change out the bound with a dummy variable, and then we take the limit as that variable goes to infinity. So this will be the limit as b goes to infinity of, this is going to be the natural log of x from x equals 1 to x equals b. So the limit as b goes to infinity of the natural log of b minus the natural log of 1, which is 0. And so the limit I dropped the absolute value here because it doesn't really matter, because this is going to positive infinity. And this is, of course, going to go to infinity. So this tells us that the integral diverges, and therefore the sum also is going to diverge. Okay. So this is probably the easiest way. There's a lot of ways to show that the harmonic series diverges, but this one's probably the easiest way because we just reduce it to the integral problem, and that allows us to use the antiderivative. So if we just take a look at the picture of what this would look like. So I'm just going to draw a rough drawing here, but you could play around with it on the graphing calculator. Okay, so let's say that this is the function 1 over x. And we have the numbers 1, 2, 3, etc. So if you look at the sequence of rectangles, or sorry, not the sequence of rectangles, but like the Riemann sums, specifically the left-hand Riemann sums here. This is what they would look like. Okay. So if we were going to find the area of all of these rectangles, in other words, if we find the left Riemann sum here, what we would find is that this is equal to 1 plus 1/2 plus 1/3 plus 1/4, etc. Right? Because that's what the height of these rectangles would be, because you'd plug them into 1 over x to get the output. And the width of all of these are 1, so we would just multiply the whole thing by 1, right? That's all we need to do. So this, of course, is equal to the harmonic series. Okay. And it's clear here that this is greater than the integral from 1 to infinity of 1 over x dx, right? Because this is an overestimation, right? So this is, every rectangle is going to be above that line. So it's actually finding more area than you would find just finding the area underneath the curve here. So because this one is diverging and this one is greater than it, this one is also, if we're looking at the limit, this one would also be going to infinity, because we have something smaller than it is going to infinity. So that means that the larger thing also has to be going to infinity, because it's always going to be larger. Okay. So that's kind of the idea here. Now, with other sequences or other sums where you do the integral test and you find that they both converge, what you'll find is that if you look at the sequence as the series of rectangles, they'll actually be underestimations. So then you'll have a reverse inequality here, and you'll find that the integral converges, and then the series is smaller. So if it's smaller than something that converges, then it also must converge. Okay. So let's go ahead and look at an example of that. So we don't need to look too far. We can just look at 1 over n squared. Okay. So this is going to be equal to 1 plus 1/4 plus 1/9 plus 1/16, etc. Okay. So if you draw out this picture, you're going to see that this is actually less than the integral from 1 over infinity to 1 over x squared dx. Okay. Again, this function right here, this will satisfy all the conditions. It's decreasing, it's continuous, and it's equal to 1 over n squared on this interval. Now, when we calculate this integral, okay, we're going to do the same thing. We're going to get the limit as b goes to infinity. from 1 to b of 1 over x squared dx. We might have done this one at some point already. I'm not sure, but always good to practice these. So this is going to be negative 1 over x, right? And this is from x equals 1 to x equals b. So this is the limit as b goes to infinity of negative 1 over b minus a negative 1, so plus 1. So when we take the limit of this part, it's just going to be 0, so we're going to get 1. Okay. So this is equal to 1. So this sequence is going to be less than, I guess we should really say less than or equal to. That would make more sense, right? Actually, you can say that this is true, but with the way that the sums work out, I didn't actually draw the picture here, but the way the sums work out, you do have to add on an extra 1 here just to get the left-hand side working properly. Or rather, it's because you're doing the right Riemann sum in this case. But anyway, the details aren't super important here. But this is equal to 1 plus 1, so we get 2. So the important thing is that this shows that this sequence is less than 2. But again, it doesn't really matter what it's less than. It's just less than something that's convergent. And then that tells us that this is also convergent. Okay, so it doesn't tell us anything about what it's actually converging to. Okay, so this one, we can get an actual number here, but we have no idea what 1 over n squared is actually converging to. And when you look at it, it actually converges to quite a weird number here. Okay, pi squared over 6. And that's equal to 1.64. So it is less than the 2. So we can kind of get an upper bound here, but we can't actually get an exact number through this method. So this is just purely a method to show whether it's converging or diverging. So you can use this integral test in any of these for any function where you could find a function that meets those conditions. But it is most often used for what we call these p-series. So a p-series is a sum of the form n equals 1 to infinity of 1 over n to the p. Okay. So we have some power of p here. So if p is less than or equal to 0, or I'm sorry, 1 rather. If p is less than or equal to 1, then the sum diverges. Okay, so we saw this with the harmonic series. I think any integer power less than 1 should be pretty obvious that it's going to diverge. Like for example, if you have p equals 0, then you just have a series of 1s. That's of course not going to converge because you're adding 1 infinitely. If you have negative 1, then you have the sum now of just n, and that's going to be 1 plus 2 plus 3. That's of course not going to converge because it's just going to keep getting larger and larger. But if p is greater than 1, then the sum converges. Okay, so it can be anything greater than 1, like even 1 over n to the 1.01, and that'll still converge. Okay, so at 1 specifically, it doesn't converge, but anything greater than it does.